Okay. All right, so today we're going to do unit 13. It should be available now. I just noticed it was hidden until just recently, so you may have to refresh that. And so we're just going to walk through this. We're going to jump up to 17, chapter 17. We just have a couple weeks left in this class. So basically there's this unit 13, then there's unit 14, and then the last week we were working on our final projects pretty well full time. So we just have to kind of look through the remaining topics that we want to cover this course and kind of select what we want to do here. So we're going to do chapter 17 this week on kind of future architectures, including quantum computing for this. So I'm just going to kind of walk through this today and have you work on the exercise. The beginning of the chapter just talks about some of the general some ways we're improving computer, or we've seen computers or processors expand or grow throughout history. So the increase in the processor speed here, the increase in the number of bits they can often process in a byte size, or on a bus here. Some increases in memory speed and I/O stuff, and they walk through this sort of stuff. Let's see if I can show this. And so we can talk about how these computers might continue to grow, and that brings us to something called Moore's Law. And Moore's Law is old, like almost as old as I am old. Okay, not as old as I am, but almost as old as I am old. And it was a prediction by a researcher at IBM called Gordon Moore about the rate that the number of transistors we were putting on a chip was growing for a number of years, for about 10 years. And then he extrapolated that and said, thought that they would continue to double the number of transistors on a circuit was doubling frequently. And I think originally it was actually 18 months. And then for a while we were saying 2 years. Now it's kind of maybe slowed to every 2.5 years, but we still see them shrinking. So one thing I want you to do today is I'm going to go through this. So I'm going to go through the readings and stuff, but in the exercise, there are questions that you can answer as we're going through this and work on. So if you go to the class exercises here and read that, you can make a copy of that and start working on that there. So one of the questions we hear a lot today is Moore's Law dead, or is it still going on for this? Again, this is a nice graphic that shows us. Now, one thing that's, I think, often confusing, this looks like a nice straight line growth. Here, Moore's Law is almost always shown as a nice straight line growth. But the reason it's a straight line growth is that this scale on the left side is exponential here. So we go from 1,000 to 10,000 to 100,000 to 1,000,000 here. So this growth is very fast here. So this is actually exponential growth, but again, we're showing it with a exponential scale here. And so it appears to be a straight line for us. And again, this starts back in the 70s with early chips and then goes today. And you can kind of see maybe that it's not growing quite as fast and steady in recent years, at least for some of the chips, as it had in the past. But it has been very consistent, but people argue that we are reaching the limits. So we have been able to make circuits smaller and smaller, make the wires and the connections smaller and smaller. So we are getting to almost the atomic scale of this, where we're worried about sending individual electrons down circuits and how much interference an electron will cause going down a wire, as far as like, an electron traveling generates a magnetic field and stuff like that. So we're working at very small scales here, and we can't continue this if we just continue to try to make things transistors smaller, because there seems to be some theoretical limits to how small transistors can be, largely tied to the size of an atom, amazingly, and how small these things actually are. So again, that's one thing I want you to look at, is this whole idea is Moore's law going to continue or not? This is a nice history of Moore's law from IBM. They did, talking about it. And predicting it. So again, this started in an original paper published in 1965 and was modified in 1975 to say basically you should be seeing a doubling every 2 years for this. And they talk about some of the changes, and you can just look at the scale of things. And on where we were talking small nanometers, and angstrom units are where we're at these days. So if you want to explore this more, there's kind of some talk about this. And again, this is another graph of the same thing, this growth of transistors here. Now, I've heard different things. When I've always in the past heard of this, it's always been the number of transistors on a single chip, a single piece of silicon that we are generating for that. Still how it is. Sometimes I talk about a package being something rather than a piece of silicon for this, because of the way that it's developed. And again, for your exercise, I just want you to find an article talking about Moore's law recently, and because some people will be saying it's dead, some people say it's going to continue on for the next 10 years. So I'd like to have you find just an article, post the URL, and quick summary: is it dead or alive for this? Or if it's if it's yeah. So one thing we are seeing as a possible way of continuing Moore's law is the adding dimensions to things. Now, I guess we do not generally do layers on a silicon chip, but we do layers on a wafer or a printed circuit board. So let's just talk a little bit about those. So your Raspberry Pi is a printed circuit board. So I should have put a picture in here of this. So these kind of green things that you often see are your printed circuit boards. And you can see, when you look at one of these, you can see the wires that connect everything for this. But often you see these wires come and just seem like they disappear here. And I was talking to my son-in-law, boyfriend-in-law, my daughter's boyfriend slash fiance, whatever that is called. He does PCB design here for lots of projects. So it's fun talking about him. And he has to lay this out and map them. And it's very three-dimensional, which I didn't realize, in that in these circuits here, you have multiple layers, like often 6 layers, and then you can drop down the different layers and run different connections. So like here, this connection might be running over here and has this little circle. That often means it may be dropping down. It's like a little elevator, as you described. You can drop down 3 or 4 layers and then keep and go on that layer. Because one thing you can't have is you can't have these wires crisscrossing here. That doesn't work. You know, electricity is not going to be happy there. So if you want them to cross or whatever, you drop down layers. So in printed circuit boards, we do layers a lot, and we have been doing layers for a while for this. So in printed circuit boards, we do layers. But now these black chips, that's just black coating over a silicone chip. Inside these chips, we don't do layers. So you know, if we talk about one of these chips inside one of these areas that's made up of silicone, these chips don't do multiple layers for it. They're very much smaller, and the connections and stuff there are much smaller than what the kind of wires we run on the printed circuit board here. So, but we are looking at adding a third dimension to our integrated circuit boards for this, and being able to do some sort of layering on these circuit boards. And that could help us out with stuff. So that's what this is talking about, is either doing layers, or like this is talking about chiplets, having like separate little chips that maybe are stacked on each other. One of our challenges though with that sort of stuff is heat. Already heat is a horrible challenge on computers because, again, we're running electricity through these very close wires, and that generates friction, and we get heat, and it's really hard to dissipate heat for. That's why we're running fans on so many things. We're getting better at stepping down to lower power circuits that don't generate as much heat, but still let us go. But heat is still an issue, and when we're doing these stacked stuff, you can imagine heat still being an issue there. Talked about specialized devices, and this is what we kind of talked about last week, although these are more specialized circuit devices. So I'm not going to talk too much about that here. Okay, so here you're supposed to research third dimension, and Moore's law is dead. So those 2 things you're supposed to look at. And then we're going to talk about quantum computing here. So kind of gives an overview, talking about the first computers were actually mechanical computers for this. You know, the analytic engine and that sort of stuff. There are really cool mechanical, calculators that work off of physical gears and stuff like that. Then we moved on to analog computers. The next set of computers were analog, so they used electricity, but they weren't digital. And we've actually, there's still talk and work with analog computing for things. I remember when I was in college, we did some analog computing sort of stuff. That was a long, long time ago. So, and now for the last, 40 years, we've really just been doing digital computing and digital logic. But is that where we're going to see the future? Is there another paradigm that we could look at? And so quantum physics comes up here and discussed it. It's compared to what we call classic physics. And you're probably aware of some of the stuff with quantum physics in that it is very probability based. And so at some point they were, working with the classical laws of physics, and they're running into issues with those especially kind of doing very small interactions with things. And so this area of quantum physics was developed, and really to explain these things. So, rather than having an electron being a part, a thing, like a particle sort of idea, electron is more described as a combination of waves, kind of a probability sphere or area for things, and that it is not. We generally we don't know where it is. We can't necessarily say where it is. We can just say where, the probability distribution of where it's at here. And then we have this whole uncertainty principle that kind of plays into this. And there's lots of, fun, strange things in the quantum world. I'm going to skip over the spintronics section here and just get into this quantum computing world. Quantum computing actually has its history in quantum physics. So Richard Feynman, not George Feynman. That was a different Feynman. Richard Feynman was he's a famous physicist and was trying to explain or work with quantum physics. And our digital computers just were not successful. So he said it would be really nice if we could just use some quantum thing to simulate these devices or these interactions, so that it would be a lot faster than if we could just do a simulation of some quantum effects, rather than having to program a simulation of quantum effects in things. It's kind of like saying, if you're going to study gravity, it's almost easier to just have a little thing where you can just drop things and measure them, rather than writing a whole computer physics engine where you would program a ball in a video game to drop. And it'd be easier just to have an actual physical simulation for that. And they didn't have any physical simulations that they could run with quantum. So he said it would be nice to invent a quantum computing. And that's kind of how this got started. So let's just talk a little bit about quantum computing then. I'm trying to figure out where to stage this as far as quantum computing goes. A couple things, quantum computing stuff that you're not going to understand, because we don't have, we haven't given you the math background, we haven't given you the physics background to understand this completely. So my job is to have you understand it somewhat. So unfortunately, you're going to leave today, hopefully this week, with knowing a little bit more about quantum computing, but not a lot about quantum computing. So just be aware of that for this. And to tell you, I'm not an expert on quantum computing. I mean, I have an undergrad, my undergrad degree is in physics. I studied physics and this sort of stuff a lot. I have a degree in math. And so I've taken a lot of math and the algebra and that sort of stuff. And so I understand that pretty well. And I know you don't have that background. But even with my background on that, this quantum computing is very complicated. So my goal is to try to get you some explanations of different parts of quantum computing that you can understand, and then also show you some of the complexity of quantum computing for this. So the first thing we want to talk about is bits and these qubits, quantum bits here. And this is what a lot of the talk on quantum computing is about, is these bits. And the idea, one approximation of this bit is that, in a classical bit, a bit is either on or off. And in quantum computing, a qubit can be somewhat on and somewhat off. Okay, and we can talk about the probability of it being on and the probability of it being off of things. So it's not necessarily all on and all off for this. And not just the probability, but the fact that it can be on and off at the same time in some ways, until later on. for things, and that helps us do this. Now, you may have heard of fuzzy logic, and you might want to kind of think of fuzzy logic. Fuzzy logic is an area of math where again, that is just probability, where we talk about, rather than something being true or false, something can be kind of true and kind of false. And we can talk about the probability of it being true or false, the likelihood of it being true or false there in this whole area of math and computing tied to fuzzy logic. And that is kind of similar to these qubits in like a two-dimensional world, but qubits live in a three-dimensional world. So it is a good analogy, but it's not all that accurate for things. I know I'm not doing a great job at this. So what we generally see with qubits is we represent them in 3 dimensions. A lot of times we represent them in 2 dimensions, but they are made up of complex numbers. So you study imaginary numbers somewhere in high school, don't you? So like the square root of -2, maybe. So again, there's these complex numbers, and complex numbers are 2-dimensional kind of numbers. They have to be plotted on, rather than on a one line, they plot on a 2-dimensional line. And we work here with combinations of complex numbers, and that pushes us into 3 dimensions. So in order to kind of understand where a qubit is, you kind of have to look at it in 3 dimensions for this. You also see this notation. We'll talk a little bit of this notation. You see this vertical line and then some symbol and then either a greater than for this, or else you'll see it the other way. You'll see a less than symbol and a vertical line there. And those are, you can think of them as 2 halves of a bracket. So this is the ket part, the right side of bracket, and the other side is the bracket, the bra part of it there. So when people are talking about these, they'll talk about the left hand or the right hand side of a bracket notation there. So okay, let's try to do a more simplified version. IBM is really big in this field, so we'll jump to a couple IBM sort of stuff here. So I'm just going to walk you through this. So actually, let's start with our textbook here. So again, our textbook talks about quantum bits, qubits. Qubits can be 0, 1 in a 0, 1 quantum system. However, they can exist in superposition. This means that there's some probability of being either of 0, 1 being observed. And this ties into this quantum property of quantum superposition, where we can have multiple states that can coexist at the same time. Our cat can be dead and alive at the same time, to quote Schrodinger. Okay. And later on, we can read this, and once we read it, then we know, oh, the cat's dead, or the cat's alive, or the bit is 1, or the bit is 0, once we look at that for this. So let's go back to IBM here. IBM tries to talk about why we might need quantum computers, and so talks about simulating quantum physics here and some uses on them. Now, one thing to be aware of is that quantum computers are not going to necessarily replace existing computers. They are not, we can't just program a bunch of logic gates and stuff like that. They're very good at simulating complex environments. So we can see them, if we're going to simulate dynamic systems or a complex environment, we can set up equations for that. Or when we want to have to do lots of kind of like, I don't want to say computations at the same time, but if we want to find try out a lot of possibilities, combinations to try to find the right combination that would solve an equation or do something. So like they're very good. Like if you had a maze, like if you had a maze and you wanted to solve this maze and find the fastest path, you can trace your finger through it. But it'd be actually very fast. Just take water and pour it into the top of the maze and let the water just flow down into all the areas of the maze. And then the water will find the fastest way through the maze. It'll just try out all the possibilities. I mean, the water will flow everywhere in the maze and it will find out where the exit of the maze is and flow out there. And once it does, then you can, grab that current and say, that's the route. So quantum computing is kind of like that. We can program in the maze and say, have it find the path through the maze, and it'll find the fastest path through it. It won't try them all out. It'll try them all out simultaneously in some ways for this. So in those sorts of simulations, they are much faster than classical computing here. But trying to figure out how we program these quantum algorithms in is very hard. So a couple things we have to be aware of. In order to get any sort of quantum effects currently, we have to have these very cold here. And again, you're thinking, oh, my computer has to be cold here. I'm kind of thinking my laptop, the fan may have failed in my laptop because it is getting really hot these days. It sits on my lap, and especially if I'm doing some machine learning or game development stuff that uses that it gets really hot. So I'm trying to get it to the end of the school year, so then I can give it back to IT and say, I think my computer's broken. But so we're trying to keep things cool. Little hot, a little cool, we know that is not what we're talking about here. These things have to be cold. Like liquid nitrogen is too warm for this sort of. Liquid oxygen is way, all these things are way too warm. We have to get this really, really cold out here. You're thinking like as cold as outer space stuff, and I'm saying no, colder than outer space like stuff here. So we need things super cooled so that we can get some of this superconductor stuff passing through these things. So you will see pictures of quantum computers, and a lot of it is some little wires in a huge refrigerator, so we can get it very, 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 very cold for this. Okay, so that's something we have to do. Here's our three key terms. So superposition. So basically, this talks about the fact that these qubits are complex in that they actually are made up. We look at them from complex numbers, and they're really in this multidimensional computational space, and they can represent something that is both on and off, or some combination, the probability, or some measurement, not even measurement of that, some way of describing these, where it is a little bit true and a little bit false at the same time, is this superposition sort of idea. I thought this had superposition in it too. Yeah. So the position, the principle of superposition states that any two quantum states can be added together and the result is a valid quantum state. So yeah, so not only can we have these qubits in the state, but we can take them and put them together, and together they make an even more complicated quantum state, but we can add these quantum states together. In my mind, it's similar to musical notes or chords, where you can imagine you playing one chord and another chord, and together you play two notes, or one note, another note, and playing two notes, and you'll get a more complicated wave for this. You can also kind of thinking of it as resonance, so if you think of you play a note on a piano versus a note on a violin, they sound different because they're resonating different because of some of the surrounding ideas. So you can kind of think of them either way there. Though these waves are kind of more complicated than sound waves, but similar sort of stuff for this. Trying to explain three-dimensional sound waves. Okay, so this is a superposition again. And so we have these qubits there, and then we can combine them. We can put them together, make more complicated state spaces. So let's talk about entanglement next. So if we have these quantum qubits near each other, they won't necessarily just be independent for this. They should correlate. So again, like physicists found that two qubits are entangled, changing one qubit can directly impact the other for this. So that's part of this whole quantum entanglement. This is what your book says. So quantum entanglement occurs when multiple particles are linked together in a manner that causes the measurement of one particle to affect the measurement of another particle. And sometimes people will talk about that this entanglement will let us transport information instantaneously along long distances, and that we can go faster than the speed of sound with that. I don't think that sort of those descriptions really capture the complexity here. What we're really doing is when we find out one part of information, we know the other part of information. It's kind of like if I had a sheet of paper with some notes in it, and I knew what the whole thing was, but then I ripped it in half and put the two places in different things here. I know they're entangled. They were one at one point. When I look at one half, that tells me what's in the other half, because I know, oh, this part's missing. That's in the other half there. Just because this other half might be far, far away, and I look at this half and I know what that other half is, I've gained that information. That doesn't mean that information has necessarily been transmitted here from a long distance for this. So that's kind of the idea, is this entanglement. We can entangle them, but when we measure, when we look at one of these particles, one of these qubits, we can tell you something about the measurement of the other particle as part of this. But again, it's not magic. It doesn't go faster than the speed of light, but it is still very useful. I'm not saying it's not useful. It is just not. Sometimes people take quantum computing and quantum physics and try to make magic out of it, and it's not. It is just really neat math for it. So times like this, I wish we were all math majors. So no, Price is going, yeah. Aren't you a math major? Are you a math major? Okay. Okay, so let's talk about interference. What we get in here is this is what caused, just interference, and like anywhere else, it's going to cause us trouble with this, any sort of noise or fluctuation or problems. And again, a lot of times these are quantum states are noisy, changing, probabilistic states, and just the fact that they're noisy and stuff, they will sometimes kind of decompose, or will get information about them, or they'll change and they'll lose this sort of quantum nature, this uncertainty that we have in them. And so it's hard to maintain that. And interference is just like, our general term for anything that is stopping us here. So for this, so we can talk about this sort of problem with trying to keep that. And one of the things we work with a lot is trying to do some error correction on these quantum computing devices, so that as we see some noise and issues with these, we can hopefully combat that by having kind of replicate it, or some sort of error correction where we know what the noise was for this. So okay, let's talk a little bit about where we could use these stuff. So one of the things that comes up all the time is quantum code breaking. One of the first big algorithms that was developed for quantum computing was Shor's algorithm, which takes. So the idea is that if you have a big number, right? If you multiply two big numbers, if I have two 4-digit numbers, I ask you to multiply them. You can solve that in a second, really fast. But if I tell you I have a really big and I want you to figure out two numbers that multiply together to give you that number, how long will it take you to do that there? It'll take you more than, here, this is just one operation. Well, just multiplying, get a calculator and multiply it. Here, we don't have a, square root's not gonna, well, square root works, that's really nice, but that's not gonna work most of the time. And so you just have to try lots and lots of different combinations for this. And this is what cryptography, is based on, is this sort of, that this is hard to know. So if these are your keys, you put them together to this, it's very hard to go from this back to your keys for things. So that, this is what runs all of our security protocols, is this prime factorization problem. Can we take this problem, and I should have mentioned that these should be both prime numbers. Can we take this number and factor it into two prime numbers for this to work here? So yeah, rather than just divide by anything, just prime number and stuff. And Shor's algorithm showed that quantum computing can do this very fast. And again, it kind of comes down to like that maze sort of idea. The quantum computer just tries out all the numbers at once, or the algorithm lays out so that these qubits can represent lots of different numbers at the same time, and then their probabilistic states can interact, and then it can find the solution very fast for this. So again, this was we talk about this all the time. Other things that we see these in, we certainly see these in, again, anything for simulation. These Feynman originally wanted these to do quantum simulations, but any sort of simulation like that, weather, financial systems, any sort of stuff where we're doing complex simulations of things, quantum computing might be able to help with those sorts of simulation stuff there. But again, they're not going to be able to do like follow instructions or, like an algorithm like that we would write with a programming language for this stuff. Okay, how we do simpler applications, need for cold. And let's talk a little bit. I'm going to dive a little bit more into quantum computing. Originally, I was going to have you do the start of this course from IBM on quantum computing. Let me just in. So again, this tries to walk you through the notation of quantum computing. I'm just going to try to walk you through the basics of this, but none of this is in your exercise or anything like this. I just want you to kind of see some of this stuff. So it kind of walks you through classical computation, talking about, bits are either 0 and 1, but they can be, we can talk about other things like a 6-sided die can have something in this set, 1, 2, 3, 4, 5, 6. If you roll a die, it has to be one of those things. And then you can talk about the probability of things. So the probability of X being 0 in this state is 3/4, and the probability of X being 1 is 1/4. And we like to write this as a vector here. What is called a column vector, where the two probabilities are on top of each other, and there's an order to these stuff. And then they introduce this notation here, this ket notation for things, a vertical line, a symbol like 0, and then looks like a greater than sign to me for this. And this means that the 0 is going to happen. And so we put a 1%, 100% chance that it's here, that the 0 is there, and a 0% chance that the 1 is there. And then in a normal bit of here, this is a 0% chance it's 0, that's the top part, and a 1% chance, 100% chance it's on the bottom, or that it's a 1. Because again, we have this vector, the top is the 0 and the bottom is the 1. So this will relate to that. And then you can talk about it even written this way, and then decompose this into these linear compositions of these functions here. And again, this is all just kind of classical computing with some arithmetic, or linear algebra, or some vector arithmetic. I don't know what you call this in here. So you can talk about that this is a 0.5% chance of it being heads and a 0.5% chance of it being tails, and this is how we represent heads, and this is how we represent tails, and it kind of introduces this notation for it. And then we can talk about operations here, and our operations, we call about functions, and we can map functions onto matrices because we have discrete values. So any function on discrete values can just be represented as a matrix, and walks you through these matrix operations that we can do, and talks about this and how we can do, like here is this is like when we talked about the bracket here. This is the bracket, and this is the ket part of this bracket notation, and we often can denote a formula or a function with this bracket notation for things. And again, we're often then building these things up into this sort of matrix multiplication. And again, I never know what words to use here, because different fields use different words for these multi-dimensional things. So you might be called vectors, they might be called matrices, they might be called tensors. So I don't know where you come from or what you learned, and a lot of it depends on your field. So like if you're in computation, machine learning, these are generally called tensors. If you're in physics, these are generally called vectors. And if you're in math, these are generally called matrices. So you have linear, algebra, and that will be working on these. So, but we do a lot of work then with these and matrix, functions on things. So then we start introducing these quantum states. And the equations start getting a little more complicated, because you see these square roots of 2 and imaginary numbers showing up. Though one of the reasons is that it's kind of like we're trying to keep these. Let me go back to this. There's this probability in this circle kind of sphere, and then you can imagine that if we're calculating distances in a sphere, we start getting the square root of 2 in some of our distant measurements to keep it within the same distance as everything else from the. I don't know if I'm explaining that very well, but in our math, we get the square root of 2 comes up all the time as some kind of factored, because one of the things in a lot of these things is the probabilities I have to add up to 1. So like these two numbers add up to 1, these two numbers add up to 1, these two numbers have to add up to 1. So to get that, 1 over the square root of 2 plus 1 over the square root of 2 is just 1. It's 2 over the square root, well, yeah, so it adds up to 1 again for us. So again, that's what we're working with here. Oh yeah, here. I guess, yeah, again, we're doing distance. I forgot to square those within this notation. Okay, so again, and then we're working with bigger numbers. Like here, they're talking about you could look at diamond, the suits and how you'd set those up, and you denote every suit with a different value here with this hexagon. So this gets complicated there, and I got to this point and said, I don't think we're going to do this. I have you walk through this in class, so this is not going to be Thursdays. And again, you don't know probability rules here, and a lot of this matrix multiplication stuff you just don't know and stuff. So now one way I thought was a pretty good visualization of this is this Medium article. See if I'm signed in. Okay. And this is an example of an algorithm or a program in quantum work. So this is what these tend to look like here. They kind of remind me of Feynman diagrams, but that might be a great example for you because you probably don't know what a Feynman diagram is either. So Feynman diagrams are how you show complicated subatomic particle transitions. And it's a really cool little diagram that shows really complicated things. And that's what this does. It is just a nice visual diagram that shows some complicated interactions for this here. And again, this talks about qubits and setting these qubits up and tries to introduce this whole idea of multiple dimensions and how you can try to visualize this. But then breaks this down into these programs are called, we do some quantum encoding here, we do some computation, and then we do some measurements for these. And this is how we break these things down a lot. And again, talking about how these qubits are measured with some probabilities and how this might work for this. And again, another way of looking at this. So I thought this, at least you see some of this notation and stuff, but I'm not going to go into much more detail than that. I'll just mention, because your book talks about it, one other area. So quantum computing tends to work with kind of quick state changes and stuff like that. And we let it try out lots of things, and then we do a measurement, and that gives us a result. There's this eidetic computing model, which is more of an slower development of this sort of stuff for this. And I, to tell you, don't have a great I'm not done a while to look at this sort of stuff. But it's the description says it's very similar to what we call finding a minimum or hill climbing or that sort of stuff, where we are trying to find a solution to a problem by slowly changing things. In machine learning, we have algorithms to slowly change weights so we can find a minimum value or a maximum value in things. It's kind of like if you are in some environment and you want to get, a hilly environment, you want to get to the bottom, the lowest level, like, where the ocean or stream might be, you might just start walking downhill and figuring out where things are. And every step you might be a different place downhill. That's sort of the whole idea here, that we are incrementally moving towards our solution in these sorts of optimization problems for this. So, it'll be interesting to see if quantum computing takes out. There's some big people who know a lot about this say that this is going to be a big thing. There are also people out there that say, there are some really hard problems that we're never going to solve for this. It'll be interesting to say. We've been talking about this for quite a while. We still see advancements, so it'll be interesting to see. I don't really have a clear idea of if it's going to be, important in the future or not here. So, okay, so that's quantum computing. Let's just talk about some other technologies that are out there. So let's talk about, like, one of the things we have to look at is just, how do you make computers more efficient? And again, we're running on silicon wires that generate heat. So one of the things is, can we make them run more efficient? So there's talk, if we can run these, if we can get some sort of superconductor that would work in this, if we can find a room temperature superconductor, that would be great. And we can put it on silicon, that'd be great. Another thing is that these carbon nanotubes, people can make these little carbon nanotubes. Can we build stuff out of those? And they can send currents very efficiently through things. But again, there's a lot of infrastructure we just don't know how to do with that. So this talks about, besides carbon nanotubes, which I'm not a big fan of, I just want to bring up some other ones I think are possible futures here. We mentioned the other day analog computing there, and I think that in some ways analog computing might be important, particularly in this, what we call neuromorphic computing or memristors. There are developments of computers. So a lot of work today in machine learning is to simulate these analog devices, are neurons in the brain. And what we do is we use digital computers to simulate them there. And so we do a lot of work trying to write algorithms that will simulate these analog circuits, very simple analog circuits. And so people have for years been saying, wouldn't it just be better to build the analog circuits similar to what the brain works on there? And it's such a common idea that almost every sci-fi series out there has some phrase that talks about that. That's a neural computer, or that's this or this, where it's some sort of special device that is builds this sort of brain-like neurons in the silicon or whatever the substrate is. And people are doing some examples of this. So this memristor again is like similar to a transistor, but also a neuron, and then it can have a little memory and it works there. So that might be a future. I'm always, every 10 years or every 5 years I hear something new about optical computing, silicon phonics or photonics, that sort of stuff. And again, this is a common thing out there when you're talking in sci-fi or reading something, is that their solution is that, it's an optical, or it's hologram is another one. I didn't put holographic memory there. I still put holographic memory up here too, sort of idea. And again, so there are labs and there are people researching this stuff. You can look for articles on this, and there are people working on all these things. And often we can do small scale things with these things. The question on all of these is, can we ramp them up? And one of the problems we have right now is that silicon is so far ahead, and the digital computer is so far ahead, and we've spent so much time on it that we just it's going to take a lot of work to get any of these other stuff to catch up. And I think one of the ways we may see it catch up is if Moore's law eventually slows down. When this stops increasing, we have to look somewhere else. Right now, Moore's law is still growing so fast that no other technology is able to catch up to it. And so it'll be interesting to see at some point if Moore's law if we don't see that growth here. And I think I'm beginning to feel that way. It used to be anytime I bought a laptop or any sort of computing device, after 2 years, it would just be so slow it wouldn't do anything. And nowadays, I seem like I'm running laptops or phones for like 4 or 5 years, and they're still pretty good. I'm just trying to think of, if I expect my current phone or my current laptop to be twice as good in a few years, what do I need it twice as good? The question is, what's going to be better? Do I need more color? Do I need a more detail on display? Do I need it faster? There, what is going to be twice? It used to be everything was twice as good. The camera that was twice as good, the display was better, it was faster, all this stuff was better there. I remember we went from 16 colors, not 16-bit colors, 16 colors to 8-bit color, and it was like, wow, that's like we have more colors than you could ever imagine. Okay, one last thing is that I just want to non-Neumann architectures. Right now, all of our computers follow this Neumann architecture, where we have memory, we have a CPU, and we have some storage, and we're pulling information in and out of memory into our CPU and processing, sending it back. And there are people who are looking at some other architectures that don't necessarily separate memory from your CPU in different areas. So that might be a possibility. Okay, you're thinking, boy, Tom did a really bad job of explaining quantum computers. I wish there's something I could do to learn about this that didn't involve Tom trying to explain this to us. So, Unit 13 activity. Oops, let me change that. So this first one is not Microsoft Azure. Okay. So you can watch different videos on this as your activity this week. So I try to do them at different levels here. So this is more, I would call the pop science level 1 here. So like this one is Cleo Abraham and Marcus. What's Marcus's last? I don't know. Famous YouTuber that you'll recognize, right? Talking about quantum computers, and they go on a fun field trip learning all about quantum computers here. And again, this is IBM's quick intro, and again, Scientific America kind of intros of this. So you can watch those. My favorite video so far is this map of quantum computing here. Because it really delves better than anything else I've seen into some of the complexities here of how this again starts very, very straightforward, but talks about a lot of how this combines and works together. And then Bill talks about how different ways we could use quantum computing, and the fact that there isn't just one way we're trying to do quantum computing, is that there's lots of different devices that we're trying to use for this quantum computing stuff. So if I had one suggestion, I would say do this option 2, so you get to watch this video. This is my favorite video here. So that's what I would suggest. But if you're more interested in some of the math part of this here, we just started talking about IBM. We looked at IBM's basic quantum computing. This is part of a whole class they have on quantum computing that you can do here. But there is a video that goes along with that thing that I just showed you, that walks you through all these equations and stuff. So if you're interested on it, and again, I have trouble understanding if this is stuff you'll know. Like, talks a lot about, again, if we have a vector row, a row vector, call a column vector, we'll get this. And then he talks about if we have a column vector and row vector, we get a thing. So again, if that is not something you can understand, that's fine. But I think from a math background point of view, the third part, that isn't a bad explanation. So you have to pick one of those 3, do it. And I'm actually taking this from another class I teach. So you just have to submit a reflection. Which activity, which videos did you watch? Something new you learned from them, something old that you already knew in them, a quote, and a question. So those are the 5 things you have to submit for this as your activity. Questions on those 2 things? So you're doing the exercise hopefully now, or you can do the exercise now. The activity you can do anytime. Thursday, we're going to do a lab in here. We are not going to do a lab. We're going to do Raspberry Pi stuff. We're not going to actually do a lab. We're going to have you start working on your final project. And so the idea is to start thinking about and working on your final project and what you might need for your final project on here. So if you can, I'll bring the Raspberry Pis down. A lot of it might be kind of starting to install software or figuring out tutorials, or what other devices do you need for this, and trying to get a start on it. We want you to get a start on it so that if we need components or we need stuff, we still have a couple weeks in order to get those. So like Nick, we were talking cars. I have a little car kit now in my office I can bring down here. But I'm still, and I've got a couple other things on order that should be here soon. And again, if you need something or stuff, again, some of you might be doing networking stuff. We might not talk about that, how to simulate some of that. And to tell you the truth, some of you are going to start on your project and it's just not going to work out, and you're going to need to change gears and go somewhere else for this. And we want to make sure we have time to do that. So we want you to get started. See if this is actually going to be feasible, doing what you want. So that'll be Thursday. We'll just be working on the lab. Will be this initial prototype of thing, right? And again, we don't necessarily need you to get anything working. We just want to get you to start seeing what is going to do, what actual exact thing. I'm going to install this software on my Pi to do this, or to set up that. So we'll talk more about that. So that'll be Thursday's class. All right. Hope you have fun, quantum dreams. I was watching so many videos last night. All night I was having quantum dreams, which are always fun. Yep.
So I'm doing the ad blocker thing.
Okay.
Can you do that on the computer skills?
So yeah, so you are, yeah, we'll talk about that one, but what you do is you set it up on your Pi, and then your pi has to be on the network. So what Laura's gonna have to do is bring, and I have at least one more wireless router here that your pi will connect to this tested out. And then we'll redirect these computers to go through that Wi-Fi network rather than the, right, but I still have to get some stuff okay from IT. How to set this up, but I think. It'll do it. Okay, but again, it's gonna involve, that's what I think we need to talk about. Yes. Right. Yes. Yes, do you want just the generic letter then? Okay, yes. Resume. Yes.
Okay, I have a background in physics, mathematics. Can you explain it? I probably don't want to do that, but
Yeah, so what kind of background do you have in physics?
mechanics,
Classical mechanics?
classical, then electricity, because you said about
Right. Yeah.
I know.
Right,
So, and like all calculus stuff, like multivariable.
right, yeah.
So, like algorithms. So,
Right, so, like, see, that's why I
because
put,
why we have spherical coordinates? Why? Because imaginary numbers were like created to like avoid three-dimensional, but
yeah,
sure.
I'm not quite sure, I think, so I think what they wanna do is they want probabilities that add up to one.
Yeah,
And stuff, right, you know,
Like
like, right, and so, I think they, so, and. Yeah, I'm not, I think what they're doing is my problem is, yeah, we're working on this coordinate system, so we often have like the linear combination of two numbers or two things. And we're doing, so we can kind of imagine that as, a vector pointing in a direction into dimensional space.
I kind of understand that we have sphere, we have like two inputs somewhere, and we calculate like the how called the like we have one vector, other vector, and we calculate the distance between them, right?
Right. Yes, but I also think it might, my understanding more specific is sort of if you have a vector and another, yeah, vector in it, but we want to bring that sum back, you know, to the unit circle so that its magnitude is still going to be one.
Yeah,
And
makes
so,
sense.
right, so I think that puts it basically kind of in spherical I mean, I think that makes it, well, also, the two things that you're doing, you know, this vector and that vector. From my understanding, those are both complex numbers. So those are complex vectors.
The complex plane.
Yeah, the complex plane. So I don't know what, I'm not quite sure in my mind, I haven't worked with that enough to know what that.
So,
means.
from my understanding, basically, complex number were created to avoid like big second derivative equations. So
Right.
probably it's like the same here,
Yeah,
because if you like actually doing that, you like will be have like, because I did like differential equations.
right.
I know what
yes.
does it mean, so you can write like so many, but if you use imaginary numbers, it will be like so less, and it's easier to solve.
Right, yeah.
So probably that's
So,
why.
right, so I suggest you
Yeah, I will see the
do
video.
that one.
Okay.
See if that one makes sense to you.
Because I still kind of get the concept, like what we have like a lot of inputs and we kind of like use superposition to like calculate the probability.
Right, again, I'm no expert, I still have, I have trouble with the
yeah.
same thing. And I really have trouble understanding these algorithms, when they do these algorithms, on how they work. For this, there's, yeah, there's a couple operators that, like, if, let me go. Yeah. So in these algorithms, they have these operators, I forget what the Hallgraph or something like that
Yeah,
operator. And it is somehow supposed to take two two classical bits or classical things
Okay.
and then put them together into a superimposed state where something can be either one or the other. So I would, if I wanted to learn more about, I would look at this operator that and how it works. And if you go through some things, you'll see this operator, this H operator. And that's what they're often doing. They're taking they start with just a regular bit, binary bit, and they put it there. Now it's in superposition where it can, again, be multiple things. So usually put it here, they're only showing one, but I thought usually you put it together with two different bits, and this creates a linear combination of those two bits.
Yeah.
And that way it can be, and the probability of it being one state or the probability of it being in the other state are together there. So when you're watching, I would pay attention for that operator.
All right.
Okay.
Yep.
Sorry, I don't know more about this, but yeah,
No, that's fine.
yeah, it'd be interesting to see what you think when you go more.
Yeah, sure. All right.
Okay,
Yeah.
yeah. Summer, are you gonna be around in the summer?
Yeah. So,
Okay, you interested? Yeah, I heard you might be interested in doing some research.
yes.